very interesting meeting to participate in, and I'm very happy to have this opportunity. Let me tell you about some work we're doing at UCLA, and first of all explain the title here. It's kind of a double entendre. Designing enzymes ab initio refers to, first of all, ab initio quantum mechanics. So this is a computational way to do high accuracy calculations. And also ab initio means, of course, in Latin, from the beginning. So we're trying to design enzymes starting from scratch, namely by designing the active site using quantum mechanics and then building the protein around that. I'm going to talk about something speculative, but really the reason that Aubrey is interested in our work, which is the possibility that we might be able to design enzymes that will be able to reverse formation of ages in proteins. And I'm going to just try to excite you a bit about future possibilities just by mentioning what we would like to do but haven't done yet. Namely, ages, of course, are modifications of proteins by sugars, and an early stage would be the result of this Amadori rearrangement after the attack of lysine on a sugar. And then, in the presence of reactive oxygen species, there are further transformations, and one of particular interest to us is the formation of these carboxymethyl lysines. This is generally not reversible. These are some pictures of some early stage glycation products. Advanced glycation products include the carboxymethyl lysine and glucosapane, which cross-links proteins and of course causes a number of problems. These are found at least in these different diseases. They have effects of loss of tissue elasticity, increased stiffening, misfolding. The targets of these glycation products are the lysines, arginines, or cysteines on proteins such as vimentins, elastins, and collagens. And a problem is that these are the result of normal metabolism. They also result in increased amounts upon aging, and in oxidative stress like head trauma or diabetes results in the formation of these as well. So our idea would be to develop catalysts that would reverse the formation of these ages. For example, a nucleophile that might catalytically remove the carboxymethyl group from the lysine and regenerate the free lysine, or an oxidative catalyst, a catalyst plus an oxidant that would remove the carboxymethyl group in a similar fashion. Let me just speculate on how this might be done. Here is a proposed catalytic site, a nucleophile, it could be a cysteine or methionine, which could attack the carbon of the carboxymethyl group upon appropriate activation by other side chains of proteins. So our approach is to try to use computational methods to determine whether such a catalytic site could be produced that would indeed cause this reaction to occur, and then to design a protein that would have that catalytic site and cause that reaction to happen catalytically. Now, that's the teaser. What I'm going to talk about in the rest of the talk, however, is our approach to designing new catalysts. I'll tell you how we do it and some initial successes, but none of these, unfortunately, have any practical application in the aging field, but perhaps demonstrate what we hope to be able to do with these techniques in the future. Now, to design a catalyst for any arbitrary reaction is not a simple procedure. It's been estimated in this article by Axe that a random protein of a reasonable number of amino acids would have 1 in 10 to the 77th chance of being catalytic or of having a function. So that's essentially 0, of course. How do we improve these odds from 0 to some finite quantity so that if one made that protein, it might have a chance of being a catalyst? Well, there are various suggestions about how this can be done and demonstrations in the literature as well. Benkovic talks about retrofitting, taking the active site from one protein, putting it in a different protein, perhaps modifying its function at the same time. Don Hilbert has talked about the so-called minimalist active site redesign, so taking a catalyst, an enzyme, and then modifying the active site to do a different kind of reaction. Our approach takes these kinds of ideas into account. The basic idea is the following. What we'd like to do is, here's just a schematic representation of an enzyme substrate and solution, an enzyme substrate complex, a possibly multi-step process, but let's say there's one particularly difficult step, and then the product and release from the enzyme. What we need to do is to lower that free energy of the transition state for the difficult step, and we use quantum mechanics, first of all, to calculate mechanisms and to look at the structures and energies of transition states of uncatalyzed reactions, and then to try to devise ways to stabilize that transition state in order to make the reaction much faster. And our tools, which I won't talk about in detail, but you'll see their application in a moment, is quantum mechanics. So we use various levels of quantum mechanics. Actually, we don't strictly use ab initio quantum mechanics, but we use density functional theory, which is a form of quantum mechanics which is proved to be especially robust for studying of organic reactions. These are techniques in which we optimize the geometries and energies of intermediates and transition states along the reaction path. The software we use is something called Gaussian O3, which actually has a very distant origination here at Cambridge. John Popel was here and started this program, developing this program when he moved to Carnegie Mellon in Pittsburgh. And then it's developed into a company and is now one of the more popular and useful ways of doing quantum mechanical calculations. With techniques that are readily available, geometries are obtained that are within hundredths of an angstrom of the experimental geometry for stable molecules. Energies with some readily accessible techniques are good to within a kilocalorie or so. That's about all I'm going to say about that, but let's turn to how we apply that to protein and enzyme design. What I'm going to describe is a so-called Insideout Protocol. It's a collaboration with David Baker at the University of Washington, and we've been doing this for about 5 years now, and you'll see the fruits of the labor so far. Here's a simple schematic of how this whole procedure works. We use quantum mechanics, first of all, to design some catalytic groups that can catalyze a reaction. I'll talk more about this one later. This is the substrate undergoing reaction, so this NO bond is breaking. And here's a catalytic dyad, and it's a model for a catalytic dyad. It's just an acetate and an imidazole to represent a catalytic dyad, the catalytic groups in the catalytic dyad, and then a hydroxyl group to stabilize a developing negative charge. So we do calculations to find the optimum geometries and whether the energetics of this are such that the reaction would go very rapidly. And we call this kind of, these catalytic groups hanging in space without any protein present, a theoretical enzyme or theozyme. So we start by calculating these theozymes. Then we use Baker's program's Rosetta match to try to incorporate this active site design or theozyme into a stable protein scaffold. So there are several hundred protein scaffolds. The active site is carved out, and then we attempt to find matches of these different groups with the side chains attached without strain in the normal protein. Then we get many of these matches. They vary in quality. We rank them and filter them with various programs. I won't talk about the details, but then we also assess whether the environment of the protein will give the appropriate pKa's for catalytic groups and so forth. Then the Rosetta design program is used to redesign the active site. We keep the catalytic groups, but then we incorporate other side chains in the region of the transition state in order to pack around the transition state, but also to lead to good packing of the protein overall. And then, when we eventually come up with designs, these are tested experimentally. So I'm going to tell you in some detail about this particular design, which has been published. Here's a simple reaction which Dan Kemp at MIT many years ago studied because of its interest from a physical organic standpoint. It's the ring opening of this nitrobenzysoxazole to form a cyano nitrophenolphthalein. And the